So our test is going to be from 4.1 to 4.4. So we had 2 sections with exponentials, and now the next 2 sections are going to be logs. Why do you think we cover logs right after exponentials? They are related. Yeah, very, very good. Y'all studied logs before, right? In Algebra 2. They should have come up. Although I heard some bad news that they didn't come up until the end of the year and maybe didn't have enough time to go through them. So this was new information to a lot of students last period, which is not bad. Not bad. I'd rather have a blank slate than you coming in with a preconceived notion about logs. So those of you who have had logs or logarithms in the past, what can you tell me about them, or how do they make you feel?
They make me sad.
They make you feel snarky. Is that what you said? Oh, what did you say? You said sad. What did you say? Sparky or snarky? Sucky. Oh, they make you feel sucky. Oh, that's not very Rachel's challenge of them to do that to you. And you sad, that's marginally better than sucky, right? Logarithms are very, very useful, and they do have a lot of properties. And it's all the properties of logs that I think cause students so much grief and anguish, but hopefully not y'all, okay? Because you're going to learn things as you go, and you'll understand logs pretty well. So logarithms are very, very important. There's always a discussion between whether you think math is discovered or invented. And I tend to fall on the discovery side of it. But logs are a notation and a convention that was invented to help mathematics make more sense. And one of the early, I should say, proponents of logs was John Napier, a Scottish mathematician. And he was a precursor to logs, I should say. He used these little wooden sticks to help with his calculations. And someone remarked that they looked kind of like carpals, like finger bones, okay? If you can kind of look at the similarity over here, okay? See his hand? Look at that. And then look at these over here. I mean, they're like the same, okay? Except that the skeleton had fewer fingers than this. Because of that, these things were called Napier's bones. Ooh, Napier's bones. But what they helped you do is to work with very large numbers or very small numbers. So back in the day before social media and Xboxes and all that stuff, people would try to make sense of the world around them. And then once that was tackled, they started looking up at the stars and under the microscope for new things to discover, right? So when you look up to the stars, the numbers that you end up working with scientifically are astronomical, right? They're huge. And if you look under a microscope, they're really, really, really small. So what logs do is they make really big numbers manageable, and they make really, really small numbers, like microscopic, manageable. And you've already had experience with that in your science class. Anytime you use scientific notation, right? Scientific notation does the same thing. Like Avogadro's number, we celebrated that a while back. It was 10 to the 23rd. 10 to the 23rd, it was 6.23 times 10 to the 23rd. The 6.23 was the mantissa, the important part of the number, and then the 10 to the 23rd just told you kind of how big that number was, right? Which would be 23 zeros after the 6. That's a pretty huge number. Same thing if you were looking at like 10 to the negative 23rd. That number's so small, by writing it in scientific notation, you're making it much easier to work with. And so that's really what logs do. They make huge numbers manageable and microscopic numbers manageable by looking at simply the relative size of that number. So everyone agrees upon a common base, like base 10 for science. And then you just say, okay, so it's going to be like 5 times 10 to the 23rd or something like that. All right, so that's a log, or the idea of a log. The log itself is actually much easier. By the way, log is short for logarithm, not logistic. We study logistic. Log is short for logarithm. A log is nothing more than an exponent. There you go. What is a log? Nothing more than an exponent. Is anyone in here afraid of exponents? Do exponents make anyone besides Will sucky? We worked with exponents quite a bit at the beginning of the year, right? And so hopefully you got over the fear of exponents and you're not afraid of exponents anymore. So if you're not afraid of exponents, you're not going to be afraid of logs because they're really the same thing. Now, log is not an arbitrary exponent. It is a very specific exponent. It is simply an exponent to which you must raise a particular base, which we'll call b for base, to achieve a desired result, which we'll call the argument. A log is a specific exponent to which you must raise a particular base, like base 10, base 5, base e, to achieve a desired result called the argument. For example, since 2 to the 4th equals 16, 4 is the exponent to which you must raise the base 2 to achieve the desired result of 16. So you can write this equivalently in log format. The log is the exponent. So see how I did that? Log equals 4. The log is, in mathematics, the equal sign is the 4, which is the exponent. What do we call the 2 in the exponential piece? What is that? The 4 is the exponent, the 2 is the base, all right? So that's going to be the same base. You write the log base as a subscript after the log. So you write that as log base 2. And what was our desired result that we tried to achieve? 16. That ends up being right there. That's the argument. We call the thing that you're taking the log of the argument. So now we have two equivalent mathematical sentences that give us the exact same information. Like the sentences, I eat a lot of peas and carrots when I'm hungry. Oh, great. Nice. I hope that fills you up. That conveys a certain amount of information to the listener, right? But you could also say, when I'm hungry, I eat a lot of peas and carrots. Thanks again. Same information, but what was different about it? The sentence structure, right? I had the adverbial clause in the beginning in the second sentence. That's all this is here. It's two different sentences that are rearranged to give you the exact same information. That's all it is. So 2 to the 4th equals 16 because log base 2 of 16 is 4, or log base 2 of 16 is 4 simply because 2 to the 4th equals 16. In the log format, here's how you would read it. If the base is 2 and the log is 4, then 2 to the 4th power is 16. Now, why have two different versions of the same thing? Well, it turns out that logs undo the work of exponential functions. So what type of function do we call that if it undoes the work of another function? The inverse, right. So just like x squared and the square root of x, x cubed and the cube root of x, those are inverse functions of each other. Exponentials and logs of the same base are going to be inverses of each other, all right? So we denote the inverse function like this, f inverse. That means it's the inverse function. So if you have a function that is exponential of the form b to the power of x, remember the values of b that are legal? For that, we just studied exponentials. The base has to be between 0 and 1 for it to be exponential decay, or greater than 1 for it to be exponential growth. The inverse function of b to the x is log base b of x. And it's the exact same base. We even read it the same way. We call it the base in both equations. And so the base for the logs has to be the same, either between 0 and 1 to be logistic decay, or logarithmic decay, or greater than 1 to be logarithmic growth, like our parent function, ln of x. That's logarithmic growth. So those are inverses of each other. So now here's, for lack of a better word, a conversion formula. It's a postulate that relates the log version to the exponential version. And I already gave this to you, but here it is in a box. Things are nice in a box, like donuts, right? When they come in a box. This is in a box, but it's almost as good as donuts. This double-headed arrow means that one side implies the other. It's a if and only if statement. We abbreviate that as IFF. So the way that works is you could start with the left by saying if log base b of x equals y, then b to the y equals x. Or flip it around, if b to the y equals x, then log base b of x equals y. So this is, again, is two different sentences that give the same information. The sentence structure is just slightly different. B is called the base of the log. Let's label it. B is called the base, just like it is for exponential. Y is the log, and then the x is the argument. It's what we're trying to achieve. B to the yth power equals x. Now, maybe back in the day, if you studied these in Algebra 2, your math teacher showed you a cute way to get from logs to exponential by traveling around the world. Some people are taught that. You start with the exponent, you say b to the yth power. B to the yth power equals x. Okay, that's great. But that doesn't really help you go backwards. You should be able to go from this, the exponential version, to the log version. And if you understand what the pieces are, you'll have it, right? So the base is b, so that's log base b. The exponent is y, so that has to equal y. It's the log. And then the x is your desired result. It's the argument. So you should be able to convert back and forth between the two. Here's another way to do it. If logs and exponentials are truly what's of each other? Inverses of each other. We've already studied composition of inverse functions, right? What happens when you compose two inverse functions back to back, Jesse? What do you get? Oh, okay. I was just jealous because I didn't get to see what was on your screen. You only showed Will. What happens when you compose two inverse functions back to back? They undo each other, right? And you get back what you started. You start with x, square a number, square root it, you're back where you started. Or I should say square root it, then square it, you're back where you started for positive values of x. Same thing here. You can actually get from one version to the other by undoing what's currently being done. So if on the left side here I am logging x base b, what do you think the inverse of logging it base b would be? Yeah, making it an exponent base b. We call that exponentiation. So exponentiation base b. Here's how you could show that. Put a b on the bottom left of each of those sides so that the two sides now become exponents. So I'm exponentiating both sides with the same base b, right? So now we have b to the log base b of x equals b to the y. What happens on the left? We're starting with x, we're logging it base b, and then we're undoing that by exponentiating base b. We should be right back where we started with what? X, right? And on the right side, you get b to the yth power. Is that the same thing we have over here on the right? It is. So that's how I want you to think about it. You could do the conversion, you could think of going around the world, but mathematically, what we're really doing is we're exponentiating both sides. Okay? When you combine, this is important. When you compose, I should say, two inverse functions back to back, you get what you started with. All right, so the same thing over here. If you wanted to go from this side to the other side, right now we're having it in exponential form. If I want to undo exponentiation, I have to log it, right? Logarithm it. So if the base is b, now I'm going to take log base b of both sides. Log base b of both sides. And look at the left side now. What is log base b of b to the yth power, do you think? I'm starting with y, now I'm exponentiating at base b, and then undoing it by logging at base b. I should be right back where I started with y, yeah? And on the right side, we get log base b of x. And that is the left side. So that's how you can go from one side to the other with relative ease, all right? The inverse operation of logging at base b is exponentiating at base b, and vice versa, all right? But you end up with the same information in either mathematical sentence. Okay, so now I'm going to show you a little bit of how to evaluate a log expression or to solve it. This is already solved for x. So it says to solve, we got x equals log base 3 of 27. Log base 3 of 27 is a number. So really what we're doing here is we're just simplifying the expression. And we're calling that expression x. So here's how you can think about it. You could tell yourself, okay, the base is 3 and the log is x. So 3 to what power of x gives us the desired result of 27? 3, right? So notice as I wrote that down, I didn't do the around the world. I didn't exponentiate both sides base 3. I just thought about it from what a log is. 3, the base, raised to what power of x gives us 27. Now, by doing that, notice you've converted it from an exponential to, from a log to an exponential. Exponentials you have more experience with, and so now it becomes almost intuitive, and I already heard the answer. What does x have to equal? 3, right? 3 to the third power is 27. So the first thing to do if you're trying to evaluate or solve a log equation is you can convert it to the equivalent exponential format. This is another way to do it. Actually, let me leave that right there. This would just be, we converted it. If we started with it like this, and you want to actually get in on this new thing called exponentiation, you can actually exponentiate it, both sides. You can exponentiate both sides. And I like this because as the problems get a little bit more difficult and less intuitive, this process will always work. All right? So what happens on the left? What's 3 to the log base 3 of 27? Should be 27, right? Because exponentiating base 3 and logging base 3 are inverses. And on the right, we get 3 to the x. Now, once you get it to this, of course, this one was intuitive. You could do the following. You could try to get the bases the same. If you're still unsure what x is, try to get the bases the same. The left side is 3 to the x. So all you have to do is then ask yourself, can I write 27 as a power of 3? And the answer is yeah. It's 3 cubed. So now because you have 3 to the x equaling 3 to the third, because you've gotten the bases on both sides the same, they're both 3, you can actually now just equate their exponents and say, so x equals 3. And it works because exponentials are 1 to 1, and it also works because really what you're doing is you're then logging both sides base 3. This is what you're really doing. You're doing log base 3 of the left side and then log base 3 of the right side. And of course, what is log base 3 of 3 to the x? It's just x. And on the right side, what's log base 3 of 3 to the third? 3. Yeah. So you don't have to show that step. This one is intuitive. You can get the bases the same, and you just know it's 3. You can go straight from here to the answer. So I showed you 2 different ways. You can either try to write the other side as a power of 3, or you can just undo it by logging base 3 of both sides. That's fine. Yeah, that's fine. You could just look at it and say x is 3. In fact, that's where I want y'all to be. By the end of y'all's practice with logs, I would like it for a problem like this for you just to say, okay, it's a log, base 3, 3 to what power is 27? Oh, the answer is 3. You go straight to the answer. I'm just showing you a lot of the behind-the-scenes work. Now, we've already seen this a couple of times, so I'm going to go ahead and kind of write it out. So far, we've seen it with different bases. B to the log base b of x should equal what for any value of b? It should be x, right? And it works the other way around, too. Log base b of b to the x also equals x. This is not the first or the last time we're going to say this. This is very important. This establishes the inverse nature of those two. You can compose them in either order, and in either case, you end up with what you started with. On the left side, you're logging it first, then you're exponentiating. You're undoing it, getting back to x. On the right, you're exponentiating first, and then logging it with the same base. You're right back where you started. Super important. Okay, part B. Log base 4 of 1 over 64 is what? Well, again, you can convert this to exponential and get the bases the same, but I want to show you another way to do it. I'm going to show you how to do it using this property right here. If you can write the argument as a power of the given base, then the answer is just going to be the exponent on the argument, because that's what a log is. So let's try this one that way. My base is 4. Can I write 1 over 64 as a power of 4? Well, if it's one that I expect you to do without a calculator, it's going to be something that works. So let's just focus first on the denominator. Keep it as 1 over. Is 64 a power of 4? Yeah, it should be. It's 4 cubed. All right, now I need to get that 4 to the numerator, so we studied exponents before. When you bring that to the top, it becomes 4 to the what power? Negative 3. And now, look what we have. We have x equals log base 4 of 4 to the negative third. What's the answer? Negative 3. There is that property. Log base b of b to the x is just x. Log base 4 of 4 to the blob is just the blob. The blob happens to be -3. So that's another way to do it. That's how you could do it without converting it to exponential. But if you don't like that, of course, you could actually exponentiate both sides. 4 to the x equals 4 to the log base 4 of 1 over 64. And then, of course, you get 4 to the x equals 1 over 64. And then from there, you would try to get the bases the same. So it's still the same work. You're just doing it in an exponential sentence instead of a log sentence. All right, this one. I want you to do this one on your own. Showed you a couple ways to do it. It is equal to a nice rational number. Good. All right, I showed you 2 of the 3 ways up here that you could do it. You do get 5 halves, okay? If you want to convert it to exponential by doing the around the world thing, then 2 to the x equals the square root of 32. You end up with that right there on the second line. You can also get to this line, I'll call this a different method, by exponentiating both sides base 2. 2 to the log base 2 of blob is blob equals 2 to the x is 2 to the x. Once you get it in exponential format, your goal is to get the bases the same. And since the base on the left is 2, you're trying to write the square root of 32 essentially as a power of 2. So if you get rid of the radical, it's to the 1/2 power. 32 then is 2 to the 5th. Raise the power to a power you multiply. So you end up with 2 to the x equals 2 to the 5 halves. And therefore, x equals 5 halves. You don't even have to show taking the log base 2 of both sides. But that's essentially what you're doing. If you can get the bases the same, you can just equate the exponents. The other way on part B is working it in a log format. Since the base is 2, just try to write the argument as a power of 2, and you would do the same things. Get rid of the fraction, write as 2 to the 5th, and now you have log base 2 of 2 to the 5 halves. That reinforces the inverse nature. Log base 2 of 2 to the blob is just the blob. So x is the blob, which is 5 halves. Love those exponents. Love those logs. Really the same thing. All right. It says fact. Ooh, facts. I love facts. It says, since f of x equals b to the x and g of x equals log base b of x are 1-to-1, they're both 1-to-1, then if you get the bases the same, gt, bt, s, b to the x equals b to the y, then x has to equal y. You don't have to bother with taking the log both sides base b. It's going to work. And it works the same way if you get the bases the same with logs. If you get log base b of x equaling log base b of y, you could just drop the logs and you can equate the arguments. You don't have to exponentiate both sides base b, but that will work, and that's why it works, okay? So you get the bases the same in exponential form or log form. You can either equate the exponents or you can equate the arguments. All right, here's an additional fact. Ooh, more facts for the buck. The previous fact was in a box. That was true. While this fact is not in a box. Yeah, cool fact. All right, so if we take a look up here before we walk away, remember I said initially that logs made huge numbers manageably small and microscopic numbers manageable again. We took this giant number of 27. Oh, that's huge, right? It's double digits. And we ended up expressing it as a single digit number 3. Okay? Now, granted, 27 is not that big, but we're practicing with small numbers. But notice what it did is it brought it down to size. You're working with just the exponents on the base of 3. So 27 is essentially equal to 3 in log land, base 3. Same thing here. We had a small number, 1 over 64. That was like really small, almost uncomfortably small. We were able to represent it as negative 3, a manageable number in terms of base 4. And on the last one here, we took the huge number of square root of 32, and we were able to represent it as just 2.5. So you can see here on a small scale now that logs take bigger numbers and make them manageably small, and it takes small numbers and makes them manageably big, I guess I should say, bigger. Let's go ahead and review some properties. Your calculator is pre-programmed to handle 2 bases directly. Base 10, which we call the common log or the common base or the scientific base, and base E, which is the one we use in here most of the time. So a logarithm with base 10 is called the common log or the scientific log, and it's denoted by omitting the subscript. So if you ever just see log of x, it is implied every time that the base, the subscript, is 10. And you've probably seen that in a science class. If you've studied light intensity, if you've studied sound intensity, if you've studied magnitude of earthquakes, Richter scales, pH tests, all of those are log equations, base 10. They're all built upon a log, all right? The other one is base E. That's the natural base. That's 2.718. And we're familiar with this as our parent function. When you see ln of x, the natural log of x, as we have seen with our parent function, it's the same thing as log base E. And your calculator can handle it directly. Any other base has to be specified. So if you want it to be log base 7, you've got to write log subscript 7. So here are some properties of all logs, which we'll do specifically for base 10, base E, and then for base B in general. Properties of common logs. Okay, so log of 1 is equal to 0. That's a fact. How do we know that? Well, what's the implied base here? 10. So what we're going to do to the right of each of these is put the if and only if. We're going to convert it to exponential. So log of 1 is 0 simply because 10 to the 0 power is equal to 1. That's what the log is. Log of 10 is 1 because 10 to the first is 10. Before we move on, let's do a couple more here. Jump up here to this little spot. What do you think log base 10 of 100 is? 2, because 100 is 10 squared, right? What do you think log base 10 of 1,000 is? Well, 1,000 is 10 cubed, so it should be 3, right? What do you think log base 10 is of 1 million? It's 6, right? You're just counting zeros. 1 million is the same as 10 to the 6. So you can see why scientists like the metric base of 10, right? The scientific base. It's really easy because we count as in a decimal system. So there you go. That's pretty cool. Here's an application of the common log Richter scale. Anyone here had the privilege, honor of being in an earthquake in your lifetime? A real earthquake? Yeah, me neither. Me neither. It's on my bucket list, though. A small one, not like a great big catastrophe one. Just small, just like where the plates kind of rattle and you go like, whoa, I think that was an earthquake. Okay? They measure earthquake intensity on the Richter scale. So you might be reading the news or watching the news and you hear about a level 2 earthquake that happened somewhere. 2 on the Richter scale. And then you read like somewhere else that there was a level 4 earthquake somewhere else. Well, the average viewer or listener, reader, is going to probably make the assumption then that, first of all, the level 4 is probably more severe. Would you assume that? Yeah, it's not like golf where the low score is actually better, and better is more destructive, right? So the level 4 is probably more intense than the level 2. How many times stronger or intense was the level 4 from the level 2? Most people would say twice, right? 2 times 2 is 4. Oh, man, the level 4, that was twice as intense as the level 2. They got it twice as bad. That's not true because the Richter scale is a decimal scale, and these right here are logs. Those are exponents. on base 10. So the intensity of a level 2 earthquake is 10 to the second, which is 100. The intensity of a level 4 earthquake is 10 to the 4, which is 10,000. How many more zeros does 10,000 have than 100? 2. In other words, what's the difference? What's 4 minus 2? 2. So what is the number with 2 zeros? It's not 2, it's 100. So it turns out that a level 4 earthquake is actually 100 times more intense than a level 2. Wow, that's pretty cool. A level 3 would be 10 times as intense as a level 2. So that's how you read the Richter scale. You find the difference, and then that becomes your new exponent on 10. Pretty cool. So now you know, right? Whenever you're talking with friends about earthquakes, you say, oh, yeah, Richter scale. It's a log scale.
How far does it go up to?
I don't know what the strongest earthquake ever recorded is, but it was probably very destructive. I'm not sure. I'm sure you can Google that right away, right? Anyone want to do that? Siri, what's the most destructive earthquake of all time, and what was its Richter scale magnitude? I don't know. 7? 5? I don't know. I wouldn't want to be there. So anyway, that's base 10. These last two here, this is just breaking it down into two separate things, the inverse nature. Log base 10 of 10 to the x is x, and 10 to the log base 10 of x is also equal to x. Okay? So that takes care of base 10. Doing the same calculations for base e. The natural log of 1 is 0. 9.4? Whoa, 9.4 was the highest recorded one. 9.4. Ouch. Okay. What's that? Oh yeah, if you want to figure out a 9.4 earthquake compared to a level 2, all you got to do is find the difference. So 9.4 minus 2 is 7.4, and then raise that, or make that the exponent on 10. So the 9.4 earthquake was 10 to the 7.4 times stronger than the level 2. Pretty intense. Pretty intense. All right. The natural log of 1 is 0, simply because e to the 0 is 1. The natural log of e is 1, simply because e to the first is e. Remember, the base of the natural log is e. Let's do a couple more right here. What do you think the natural log of e squared is? 2. Good. What's the natural log of e cubed? 3. So on and so forth. Okay, got it? And then these last two again, very important. This again captures the inverse nature of e to the x and ln of x. Natural log of e to the x is x. E to the natural log of x is x. It's the same thing we did right here, except with base e. So your calculator handle those directly. In general, base b, log base b of 1 is 0. That means all functions that graph in the form log base b of x, they all pass through the point 1, 0, just like our natural log function did. So natural log, or log base b of 1 is 0, because b to the 0 is equal to 1. And again, those are your legal bases. Anything between 0 and 1, anything greater than 1. Log base b of b is always equal to 1, simply because b to the first is equal to b. And in general, I have some room right here. What do you think log base b of b squared is? 2, right? And log base b of b cubed? 3, so on and so forth. Got it. And then this right here, this is now the second time we've seen this. In general, log base b of b to the x is x, and b to the log base b of x is also x. This captures the inverse nature of those two. All right. Let's try evaluating these now. These are kind of like we just, Yeah, we could do this. Log base 7 of 7 to the 3x plus 2th power. 3x squared plus 2. Good, yeah, 3x squared plus 2. Log base b of b to the blob is the blob. It doesn't always have to be plain old x. X is boring. Log base 7 of 7 to the blob is just the blob. What about on part B? Natural log of e to the x? It's just x. Excellent. 5 to the log base 5 of 5x. is just 5x. E to the natural log of x is just x. Log base 22 of 22 to the x is x. Excellent. And 57 to the log base 57 of x is x. Good. Y'all are getting the swing of things. That was example 2. Example 3, evaluate now. So this is similar to the first one where I had it equal to x and I said solve. When I say evaluate, it just means write it in terms of a nice rational number. Log base 5 of 1 is what? 0. So the way you want to really think about it is 5 to what power is 1? 0. If you want to write 1 as the power of the base, as we did before, you can write 1 as 5 to the 0 power. Either way, it comes out to be 0. If you want to say it equals x and then convert it, 5 to the x equals 1, get the bases the same, okay, and then write it like that. But hopefully you don't do that. You just say, okay, 5 to what power is 1? 5 to the 0 power is 1. Okay, good. Log base 1/2 of 1 is what? 2. 1/2 to the second power is 1? 0 again, right? Yeah. Good. Right, that's what a log is. He was jumping him down. He wanted to. Remember, we're saying, instead of reading it as log base 1/2 of 1 is something, you could say 1/2 to what power is 1? 1/2 to the 0 power is 1. What is log base b of 1? 0. Okay, again, because b to the 0 for any legal base is 1. So those are really all the same question, just with different bases. All those log functions pass through the point 1, 0. They all have the same x-intercept. Let's write that right here. Anything of the form log base b of x has an x-intercept at 1, 0, just like your natural log parent function. Remember, it passed through the point 1, 0. Log of 1 for any legal base is 0. Always, because that base to the 0 power is 1. Sweet. All right, moving up now. Log base 12 of 12. It's 1, because that's the exponent on the 12. Log base b of b. 1. Yeah. Natural log of e. 1. Because remember, this is the same as log base e of e. So in the immediate temporary case, if you need to write that as log base e of e, so you can see it's 1, that's fine. But in the future, hopefully you just know, oh, it's base e. Natural log of e is 1. What's log of 10? 1. And again, if you want to write it as log base 10 of 10, that's fine. Cool. So summary. We're doing a lot of summarizing here. Must be important. The top one is your conversion formula. It's the sentence structure that's different that gives you the same information. The two most important points really are the point 1, 0 and base, 1. All right. So log base b of 1 for any base is 0. Log base b of b is 1. And then this last one down here again for like the third time is the important relation between the inverses. Compose them back to back in either order, you'll get what you started with. Okay. As I already mentioned, your calculators are pre-programmed to work in either base 10 or base e. So if you would like to now, grab a calculator. We got 15 minutes left. We're going to do some stuff on the calculator now. No, yeah, we do. Don't we? No. 10 minutes. It's Rachel's challenge day, too. All right, let's go back to quickly. Let's go back to this one. We did this one early. Log base 3 of 27 we said was equal to what? 3 to what power is 27? 3. Your calculator, if you have math print, and I think everybody in here does have math print, here's what you could do to evaluate it. If you hit the alpha button and then go to F2, your window, look at it, number 5. Number 5 says log base. This is pretty nice because the 83s couldn't do this. If you select that from the F2 menu, it gives you a box to fill in for the base as a subscript and the argument. So if you want to just type in a 3 for the base and then a 27 for the argument, when you hit enter, you should get 3. Yay, it works. Okay, nice. Before your calculator was able to allow you to input things that way, you had to write all of your questions to evaluate logs in terms of base E or base 10. Now, on your calculator, the log button to the left of the 7 is log base 10. And interestingly enough, notice the second key option on there. It's 10 to the x. So they're putting the inverses on the same key. Right below the log to the left of 4 is your natural log button. The second function to that is e to the x, the inverse. Okay, there is something called the change of base formula. So I'm going to give this to you right now. It allows you to change the current base of the log to any base that you want. So if you start with log base b of x, if you want to convert it to natural log, it's just the natural log of x over the natural log of b. That's the log of the argument over the log of the base. Notice it's easy to remember because in this format, the base is a little bit lower than the x. In the ratio, the base is in the bottom and the x is in the top. If you want to convert it to base 10, it's the same to say log of x over log of the base. And in general, if you choose any other base, like a, then it becomes log a of the old argument over log base a of the old base. So for that, let's look at this little example. If you wanted to convert this to natural log, that's the same as the natural log of 27 over the natural log of 3. It should be the same as log of 27 over log of 3. And I'll show it to you right now, why it works, or that it works. Alpha y equals gives you your horizontal division bar. We'll do the natural log of 27, close the parentheses, and then you divide it by the natural log of the old base, and you get 3. You do it for logs, do the same thing. That's base 10. You get log of 27, the old argument, divided by log of the old base 3. And you get the same answer. Now notice this does not mean, since they give you the same ratio, it doesn't mean that the natural log of 27 is equal to log base 10 of 27. Because two ratios can have the same simplified result without being equal, like 1/2 and 4/8 and 50/100. But they do give you the same ratio. In fact, look at this. Alpha y equals. Since we have the option now of going alpha window 5, let's choose a funky base, like 1 divided by 22. That's a funky base, right? Let's say I wanted to convert log base 3 of 27 to log base 122. That would be log base 1/22 of the 27 divided by, do it again, alpha window 5, log base 1 divided by 22 of 3. And you still get the same answer. Neat. So right now the change of base formula is nice to have, but because your 84 can compute it directly with the alpha F2 command, it's not necessary. But there is another use for it later on. Let me go ahead and just write this one down since we did it. Log base 1/22 of 3. All right, so now let's look at example 4. We want to evaluate these on the calculator, and we want to think about a reasonable answer first. So these I wouldn't expect you to get the answer without a calculator. So we're saying 0.5 to some power is equal to 14. All right? Well, let's think about it. If I started using values like 1, 2, and 3, that's like 1/2 to the first, that's a half, a fourth, an eighth, a 16th. That's not making this number bigger towards 14. It's making it smaller. So instead of a 0.5, let's think about the bases being 1/2. I would want to flip that. If I can make that a 2, now 2 to the first is 2, 2 cubed is 8, 2 to the fourth is 16. That's going in the right direction. What does my exponent have to be in order to flip it? It has to be a negative number. So I know it's going to be a negative something. And then, of course, now that it's powers of 2, 2 cubed is 8. That's too small. 2 to the fourth is 16. That's too big. So it has to be somewhere between 3 and 4, right? So it's going to be -3 point something. All right, so that's the reasonable answer. And I do want you to think about that before we start. So now I could just type it in. The natural log of 14 divided by the natural log of 0.5. And you do end up with negative 3.807. Now, I do want you to show the change of base formula. So I'm going to write this natural log of 14 over the natural log of 0.5. Negative 3.807. Negative 3.807. All right, the next one. Log base 6 of pi. 6 to what power is equal to pi? Well, 6 to the 0 power is 1, right? Which is too small. 6 to the first power is 6, which is too big. So my answer has to be between 0 and 1. Would you agree? 6 to the 0 is too small. So, again, you can write it on your paper, natural log of pi divided by the natural log of 6. And if you type that in, anyone have it already? If you don't use the horizontal division bar, that's fine. You just got to make sure you close. You got to close the parentheses. So you get 0.638. Remember, 3 decimal places. And then finally, the last one here, as the bell is approaching, we'll get it in there. 3.6 to what power is 17? Well, if 3.6 is close to 4, 4 squared is 16. That's too small, right? 4 cubed is 64. That's way too big. So it's got to be about 2 point something, and probably closer to 2 than 3. So what you'll write on your paper is the natural log of 17 over the natural log of 3.6. And then all you got to do is type it in. Natural log of 17, close parentheses, natural log of 3.6. I want you to think of a reasonable answer before you start, not just to see if you typed it in correctly, but that makes a great quiz question without a calculator. Log base 3.6 of 17 falls between which two integers? 2 and 3. Log base 6 of pi falls between which two integers? 0 and 1. Log base 0.5 of 14 falls between which two integers? Negative 4 and negative 3. You should be able to come up with that without a calculator because you understand what a log is. It's just a what? Exponent. Yeah, very good.